Imagine a whisper carried across an unimaginable distance, a silent message from a cosmic shore we've never seen. This December, that whisper becomes a visible reality. An object born around a star light years away is about to make its closest approach to Earth. It's a moment that transcends astronomy, inviting us to ponder our place in a universe far richer and more mysterious than we often conceive. Mark December 19th on your calendar. Circle it. This isn't just another date, it's a cosmic appointment. On that day, an emissary from beyond our solar system will perform its closest celestial dance with Earth. Right now, as you hear these words, an object that has journeyed through the infinite darkness between stars is hurtling towards us at speeds our human minds struggle to grasp. What makes this particular encounter truly unprecedented isn't just the visitor itself, but our readiness. We possess an arsenal of advanced instruments from the venerable Hubble to the revolutionary James Webb Space Telescope. We've had months of observation, a luxury denied to us during the fleeting visits of previous interstellar guests like Oumuamua and Borisov. This is our extended invitation to a cosmic neighbour. Stay with me as we unravel the enigma of 3i Atlas. We'll explore why December 19th isn't just a peak observation window, but a profound opportunity to glimpse the universe's untold stories. This isn't about fear. 3i Atlas poses no threat. It's about a deeper understanding, a moment of profound scientific and philosophical reflection that may not recur in our lifetimes. The object carries a designation that sounds cold and technical, 3i Atlas. The I signals its interstellar origin, while the 3 marks it as only the third confirmed visitor from beyond our sun's gravitational embrace that humanity has ever detected. Think about that for a moment. Just 3. In all of human history, with all our telescopes, satellites and observatories meticulously scanning the heavens, we've confirmed a mere trio of objects that journeyed here from another part of the galaxy. The first Oumuamua in 2017 was a bizarre, elongated entity that fueled endless scientific debate. Was it a comet, an asteroid, or something else entirely, perhaps even artificial? Its unusual acceleration upon leaving our system only deepened. The mystery remaining a tantalizing question mark in our cosmic annals. Then came Borisov in 2019, a more conventional icy comet that behaved largely as expected, offering reassurance in its familiar patterns, yet still a wondrous visitor from another star. And now we have 3i Atlas approaching us right now. It's different from both. December 19th is special, not merely because it marks 3i Atlas's closest approach to Earth. It is our fleeting window, our singular chance to aim our most sophisticated instruments at an object that carries within its very atoms the ancient tale of another star system, another distant corner of our galaxy. After December 19th, 3i Atlas will resume its journey accelerating as it escapes the sun's gravitational pull, destined to leave our solar system forever. We will never see it again. No human alive today will get another chance to study this particular visitor. This creates real scientific stakes, historical implications that resonate far beyond the immediate thrill of discovery. But here's where the narrative truly intertwines science with intriguing possibilities. There's a vibrant debate currently unfolding within the astronomical community. It's a tension between the prevailing scientific consensus and a more provocative suggestion from a prominent Harvard professor. On one side stands the mainstream view. 3i Atlas is a natural comet, an icy wanderer from another star's planetary system, behaving mostly as expected during its temporary passage through our cosmic neighbourhood. A magnificent natural phenomenon. On the other side, we find Dr. Avi Loeb, a respected astrophysicist and former chair of Harvard's astronomy department. He posits a far more audacious question. Should we entertain the possibility that 3i Atlas might not be entirely natural? Could it, in his words, be an artificial object, perhaps even a mothership carrying smaller probes? Before we rush to dismiss this as pure science fiction, or prematurely embrace it, let us look at the evidence. We will examine what our telescopes are actually revealing, what December 19th promises to unveil, and why this debate holds such significance. We will explore both the conventional explanation and the controversial hypothesis, allowing you to form your own informed conclusion. For that is the essence of true science, not blind acceptance nor knee-jerk skepticism, but understanding built on data and critical thought. Wherever you are on this planet, North America or Europe, Asia or Australia, Africa or South America, you are part of this global moment. December 19th is an event that transcends borders, languages and cultures. We're all standing on the same Earth, looking up at the same sky, watching the same interstellar visitor. This collective gaze, this shared wonder is rare and incredibly powerful. What could really happen on December 19th? Our aim is to answer this question not with wild theories, but with the actual science. The observations and the data being meticulously gathered by space agencies worldwide. We will separate what we definitively know from what we suspect, what's confirmed from what's still debated and realistic possibilities from pure fantasy. I promise you the truth itself is compelling enough without embellishment. This isn't a doomsday prediction. The sky is not falling. 3i Atlas poses absolutely no danger to Earth. None. At its closest approach, it will pass approximately 270 million kilometers, 1.8 AU, from Earth, roughly 1.8 times the average distance between Earth and the Sun. There is no risk of collision, no threat to our satellites, no cause for alarm. The absence of danger, however, does not diminish its significance. In fact, its importance lies precisely in the unparalleled knowledge it offers a chance to peer into processes, compositions and histories that exist far beyond our Sun's immediate influence. Scientists at NASA, the European Space Agency and observatories in Chile, Hawaii, and dozens of other countries are currently training their instruments on 3i Atlas. They're watching it daily, hourly when possible, meticulously tracking its trajectory, measuring its brightness, analysing its composition, and documenting its behaviour. And what they're observing is truly fascinating. It's complex. In some ways, it aligns perfectly with expectations, while in others, it presents subtle surprises. The object is active. Astronomers say this means 3i Atlas has a glowing atmosphere, a coma composed of gas and dust, which is being released as the object draws closer to the Sun and heats up. This behaviour is classic for comets. It's the result of ice sublimating, frozen materials turning directly from solid to gas without a liquid phase, a phenomenon we've witnessed countless times with comets born within our own solar system. But here's what makes 3i Atlas particularly intriguing. Its activity has been steadily increasing, ramping up as December approaches. The pattern of this increase, its timing, the specific way it's brightening, and how its coma is expanding, is where the scientific questions truly begin to unfold. When scientists study a comet, they're not just noting if it has a tail or if it glows. They're comparing its behaviour against sophisticated models, against decades of observations of thousands of other comets. They ask, does this make sense given what we know about ice dust, solar radiation and orbital mechanics? Most of the time, the answer is a resounding yes. Comets usually adhere to the elegant laws of physics. But occasionally there's an anomaly, a discrepancy, something that doesn't quite fit the standard paradigm. And that's when science truly ignites, when harder, more profound questions are asked. With 3i Atlas, many elements align perfectly. Its hyperbolic trajectory, for instance, is precisely what one would expect for an interstellar object, gracefully navigating our solar system under the Sun's gravitational embrace. No surprises there. Its composition, derived from spectroscopic analysis, reveals elements consistent with comets: water, ice carbon compounds, silicates. Again, no immediate red flags. But then there are the details. The precise timing of the activity increases the specific wavelengths of light it emits, and its subtle acceleration not just from gravity, but from the rocket effect, where escaping gas provides a tiny directional push that ever so slightly alters its speed and trajectory. These are the nuances where mainstream and controversial interpretations diverge. Dr. Loeb, scrutinizing these details, asks, could there be more to this story? Could some of what we're seeing be explained not merely by natural processes but by something intentional? He wonders if the observed activity transcends simple ice sublimation, hinting at a controlled phenomenon. He's not claiming certainty or offering definitive proof. Instead, he's embodying the true scientific spirit, asking if we should genuinely consider all possibilities before prematurely ruling them out. This question, regardless of one's agreement, is profoundly worth considering. The mainstream astronomical community examining the same data largely concludes, everything we're observing can be explained by known physics. There's no need to invoke extraordinary explanations. They argue that the activity patterns, while interesting, are within the bounds of expected cometary variability. The composition aligns with expectations. The trajectory faithfully obeys the laws of gravity and momentum. Apply Occam's razor, they assert. The simplest explanation that fits the evidence is usually correct. In this instance, the simplest explanation is a natural comet from another star system passing through ours. Nothing more, nothing less. So we have two distinct perspectives, two frameworks for interpreting the very same observations. December 19th stands at the epicenter of this debate, as it represents our prime opportunity to gather the best, most detailed data. When 3 Atlas is closest, our instruments will have their clearest view. The information we collect might not entirely settle the debate, but it will undeniably inform it. It will either reinforce the natural comet hypothesis, or potentially unveil anomalies that demand deeper, more challenging explanations. And that is why this moment truly matters. That is why December 19th is far more than just another date on the calendar. It is a cosmic deadline. After this day, 3i Atlas will begin its irreversible journey away from us, accelerating as it escapes the sun's gravitational grasp, heading back into the silent void between stars. Each day post-December 19th it will grow dimmer, harder, to observe less accessible to our instruments. Eventually, within months, it will vanish from our sight entirely, becoming a mere faint point of light lost in the immensity of space, too distant for even our most powerful telescopes to track. The window will close. The opportunity will end. Whatever we fail to learn before that closure will remain unknown, perhaps forever. So this is our stage, an interstellar visitor approaching its closest point to Earth, the scientific community watching intently a profound debate about interpretation, and a singular date that signifies both a climax and a farewell. In this exploration, I want to guide you through the story, piece by piece. We'll delve into what 3i Atlas truly is, its cosmic origins, and what makes it unique among the handful of interstellar objects we've ever identified. I'll walk you through the real-time observations from our most powerful telescopes, explaining what the data tells us and what mysteries it leaves tantalizingly ambiguous. We'll examine the December 19th event itself, what will actually occur, what we might observe, and the critical knowledge scientists hope to extract. Then I'll present both sides of the interpretation debate fairly and thoroughly, so you understand not just what people believe, but the underlying reasons for their convictions. Before we go deeper, I have a request for you. If this topic truly captivates you, if you're curious about the ongoing narrative of 3i Atlas and what December 19th means for our cosmic understanding, please hit that like button. It helps this video reach others who share your sense of wonder. And tell me in the comments below, where are you listening from? What part of the world do you call home? I'm genuinely intrigued to see how global this shared curiosity for cosmic mysteries and interstellar visitors truly is. This is a global moment, and that connection should be reflected in our conversation. If you wish to stay updated as December 19th draws near, if you want to follow the scientific discoveries and the unfolding story, subscribe to the channel and turn on notifications. This isn't the last we'll be discussing 3i Atlas, not by a long shot. Let's begin with the visitor itself, with what makes 3i Atlas so exceptional among the few interstellar objects we've had the privilege to observe. Imagine standing on a vast ancient beach, billions of grains of sand beneath your feet, the ocean stretching endlessly to the horizon. Waves roll in one after another, each carrying traces of distant shores. Now envision spotting something entirely different among those waves, something that didn't originate from any beach, something that travelled across an entire ocean from a continent you've never seen. That, in essence, is what 3i Atlas represents. Except, the ocean is the vastness of space, the distance is measured in light years, and the shore it came from orbits a star we can barely identify, let alone name. When astronomers label an object with that I for interstellar, they are making a profound statement. They are declaring that this object does not orbit our sun. It did not form in our solar system. Its true origin lies somewhere else in the galaxy, within a planetary system around another star. Through some cataclysmic process, billions of years ago it was ejected, flung out, sent wandering through the immense void between stars. Contemplate that journey for a moment. 3i Atlas has been traversing interstellar space for longer than our species has existed. Longer than mammals have roamed Earth, perhaps even longer than complex life has graced our planet. It has drifted through the unimaginable darkness, the profound cold, through regions of space so empty that the nearest atom might be meters away. All this time it has carried within it the immutable chemical signature of its birthplace. We don't know its exact parent star system. The distances are too immense, the timescales too vast, the gravitational influences too complex to trace its path backward with absolute certainty. But we know it came from out there, from one of the hundreds of billions of stars in our galaxy. And now, by pure chance, by the random geometry of its trajectory and our sun's fleeting position in space, it is passing through our immediate neighbourhood. This isn't just rare, it is astonishingly unlikely. Space is so inconceivably vast, solar systems so profoundly distant from one another, that the odds of an interstellar object passing close enough to Earth for us to study it in detail are astronomically small. And yet, here we are. Here it is. Oumuamua was the first. Its name, meaning scout or messenger in Hawaiian, was fitting for humanity's inaugural confirmed interstellar visitor. Discovered in 2017 by the Pan-STARRS telescope, Oumuamua instantly ignited excitement and confusion across the scientific community. Its shape appeared strikingly elongated, like a cigar or potentially a disc, depending on interpretation. Its surface seemed reddish, hinting at the presence of complex organic compounds. Most perplexing was its trajectory, which showed a slight unexplained acceleration as it departed our solar system, sparking an endless debate. Was it outgassing like a comet, yet without a visible tail? Was it being propelled by solar radiation, pressure on an unusually flat surface? Or was it, as some boldly suggested, something else entirely? We never received definitive answers. By the time we truly grasped what we were observing, Oumuamua was already receding, too distant for detailed study. We had a glimpse, a tantalizing whisper, and then it was gone. Borisov followed, discovered in 2019 by amateur astronomer Gennady Borisov using a telescope he built himself. Unlike Oumuamua, Borisov was immediately recognizable as a comet. It displayed a clear coma, a distinct tail, and spectroscopic signatures perfectly consistent with water ice and carbon monoxide. It behaved exactly as cometary physics predicted. In many ways, its normalcy was reassuring. It confirmed to scientists that while interstellar objects are rare, they can also be fundamentally ordinary, natural icy bodies that adhere to well-understood physical laws. Borisov was exciting because of its interstellar origin, but it was not mysterious in its behaviour. It was simply a comet doing comet things. And after months of dedicated observation, it too departed, receding back into interstellar space, leaving behind a wealth of data but no major controversies. Now we have 3i Atlas. From the very moment of its discovery, scientists recognized that this encounter would be different, not necessarily because it behaved strangely, but because of its timing. We found it early enough, Oumuamua was discovered already on its outward journey, giving us mere weeks of observation before it faded beyond detection. Borisov offered a few months a better window, but still limited. 3I Atlas, however, was spotted, while it was still approaching months away from its closest points to both the Sun and Earth. This early detection fundamentally altered the game. It bought us time to plan, time to coordinate, time to deploy humanity's most powerful instruments and keep them trained on this visitor for an extended period. The discovery itself emerged from systematic sky surveys, vast networks of telescopes that photographed the same regions of space, night after night, diligently searching for anything that moves, anything that changes, anything that deviates from previous images. When 3I Atlas first appeared, its trajectory immediately stood out. Not because it looked strange, but because when astronomers calculated its orbit, they found it was hyperbolic. This is the unmistakable technical signature of a path unbound by the Sun's gravity, a trajectory that enters our solar system, makes its closest pass, and then leaves forever, rather than looping back in an ellipse. Hyperbolic orbits are the definitive hallmark of interstellar objects, the precise characteristic that distinguishes visitors from permanent residents. But here's what truly elevates 3I Atlas's importance. It is among the brightest and most active interstellar objects we've ever studied, providing us with one of our best observational opportunities, accompanied by months of crucial tracking time. When Oumuamua passed, it was faint, relatively small, and by the time we recognised its significance, already too distant. Borisov was brighter and more cooperative, yet its closest approach to Earth still kept it farther away than optimal for detailed scrutiny. 3I Atlas, in a remarkable cosmic alignment, threads a unique needle. Its trajectory brings it sufficiently close to Earth that even medium-sized telescopes can observe it effectively. Its inherent activity level makes it bright enough to study in exquisite detail. And most critically, the timing of its discovery granted us months, rather than mere weeks of precious observation time. These factors combine to create the finest opportunity we have ever had, and quite possibly the best we will have for decades, to meticulously study an object born from another star system. What does it actually look like? You won't see it with your naked eye unless you possess exceptional vision and know precisely where to look under perfectly dark, unpolluted skies. But through telescopes, 3I Atlas reveals itself as a fuzzy patch of light, a luminous blur with a faint ephemeral tail extending behind it. That blur is the coma, the transient atmosphere of gas and dust encasing the solid nucleus. The tail forms as the relentless solar wind and radiation pressure gently push this liberated material away from the Sun, sculpting the classic cometary form we all instantly recognise. Colour analysis suggests a slightly bluish hue, which provides scientists with clues about the light-scattering properties of the dust and gas it's expelling. Spectroscopy. The technique of splitting light into its component wavelengths reveals the unmistakable presence of familiar molecules, water, various carbon-based compounds and silicates. These are the fundamental building blocks of comets, the very same substances we find in icy bodies throughout our own solar system. Thus, in many respects, 3I Atlas looks like a comet, acts like a comet, and possesses the composition of a comet. This is precisely what most astronomers anticipated when they embarked on studying the third confirmed interstellar visitor. It turns out the universe efficiently produces comets everywhere. Around other stars within other nascent planetary systems, the same fundamental processes occur. Gas and dust slowly collapse into rotating disks around young stars. Within these disks, planets coalesce and form, and in the frigid outer reaches, far beyond where rocky planets can form ices, accumulate water, ice methane, ice ammonia, ice. These icy bodies, through the chaotic ballet of gravitational interactions with nascent planets, can sometimes be flung entirely out of their home systems, becoming solitary wanderers, interstellar nomads, objects, precisely like 3I Atlas. This represents the mainstream scientific view, and it is profoundly compelling because it requires no new physics, no unknown processes, and no extraordinary circumstances. It posits that 3i Atlas is exactly what it appears to be a natural consequence of planet formation around another star now merely passing through our solar system by chance. But mainstream does not equate to guaranteed, and compelling does not mean certain. For while 3i Atlas broadly fits the cometary profile, there are subtle details, nuances and patterns in the data that some scientists find remarkably intriguing, while others deem them perfectly explicable within existing frameworks. The rate at which its activity has increased, the specific ways its brightness has changed as it approached the sun, the precise timing of when its coma developed, these aren't necessarily red flags. Rather, they are yellow flags, moments where scientists pause, noting interesting. Let's investigate further. December 19th is our moment for that closer look. It's when this visitor from beyond will make its nearest pass, when every telescope aimed at it will capture the sharpest images, the most detailed spectra, and the highest quality data we will ever obtain. What that data reveals could either affirm everything we currently believe about comets and interstellar objects, or it could surprise us. It could unveil some behaviour, composition or characteristic that doesn't neatly fit into our existing models. And that fundamentally is the enduring beauty of science, the exhilarating thrill of discovery. You never truly know until you look whether the universe will conform to your expectations or profoundly challenge them. 3i Atlas is more than just an astronomical object. It is a messenger, a tangible sample from another region of the galaxy, delivered directly to our cosmic doorstep by the elegant mathematics of celestial mechanics. Studying it is akin to deciphering a letter, written in an unfamiliar language, striving to understand its message about its origins, the conditions that exist there, and whether the processes that formed it mirror those that shaped our own solar system. Every measurement, every spectrum, every photograph adds another word to that translation, another vital piece to the vast puzzle of how planetary systems form and evolve across our sprawling galaxy. And so scientists worldwide watch. They track, they analyse, and they prepare for December 19th, knowing that date represents the zenith of information, gathering the moment of closest approach, our best chance to truly read the message this silent visitor carries. Let me now unveil what those powerful telescopes are actually seeing right now, what cutting-edge instruments are being deployed, and the discoveries that have already begun to emerge. At this very moment, multiple space-based telescopes and dozens of ground-based observatories across the globe are fixed upon 3i Atlas. This is no casual observation. It is a meticulously coordinated international campaign involving some of the most advanced scientific instruments humanity has ever conceived. NASA's venerable Hubble Space Telescope, still functioning exquisitely decades after its launch, has dedicated significant observation time to this interstellar visitor. The James Webb Space Telescope, the most powerful infrared observatory ever constructed, has also penciled 3i Atlas into its coveted schedule. The European Space Agency's mission's ground facilities nestled in the high-altitude dry air of Chile, and radio telescopes capable of detecting emissions invisible to human eyes. All of them are watching. All of them are diligently gathering data, and what they are observing is both remarkably familiar and profoundly fascinating. When 3i Atlas was first detected, it appeared as a subtle bluish blur, a fuzzy patch of light against the profound blackness of space, slowly shifting its position night after night against the backdrop of fixed stars. That blur immediately signaled something crucial to astronomers. This object possessed an atmosphere. It was not a bare inert rock or a solid chunk of ice. It was actively releasing material, forming a nebulous cloud around itself, and that cloud was scattering sunlight in a way that imbued it with both colour and diffusion. This was the initial confirmation that 3i Atlas was active, responding to solar heating, thus aligning with the fundamental profile of a comet rather than a dormant asteroid. But comets are not static entities. They are dynamic. They evolve continuously as they draw closer to the sun, as the heating intensifies, as more ice sublimates and liberates gas and dust. What scientists anticipated, and what they are indeed observing, is a palpable increase in activity. As 3I Atlas approaches, its luminous blur is growing, its coma is expanding, and its overall brightness is steadily increasing. These are textbook behaviours for a comet on its pilgrimage toward perihelion, the point in its orbit where it passes closest to the Sun. Literally every day, 3I Atlas appears a little brighter than it was the day before, a little larger, a little more active. This measured progression can be precisely quantified and compared against established models and predictions. Hubble's observations in particular have been invaluable. Hubble excels at visible light imaging with unparalleled resolution. Despite being an older instrument by modern space telescope standards, its capacity to capture sharp images of relatively bright objects remains unmatched in many respects. Hubble has meticulously tracked 3I Atlas's transformation from a faint smudge into a structured object, revealing a clearly defined coma and an emerging tail. These images are not just aesthetically pleasing. Each pixel is a repository of data conveying information about the material being released, the density of the coma, and how the object's rotation might be influencing its appearance. Then there is Webb. The James Webb Space Telescope operates primarily in infrared wavelengths, which is precisely ideal for studying a cold object actively releasing frozen gases. Infrared light reveals temperature shows heat and can detect emissions from molecules that might not shine brightly in visible light, but glow distinctly in the infrared. Webb's observations of 3I Atlas are meticulously designed to answer fundamental compositional questions. What specific molecules are present in the coma? Is water the predominant volatile? Or are there significant quantities of other frozen substances like carbon monoxide, carbon dioxide, or methane? Are complex organic compounds present? Webb possesses the unprecedented capability to provide these answers with a precision that was unimaginable just a few short years ago. And these answers are profoundly important, because composition offers crucial clues about the formation environment of the object. Different molecules freeze at different temperatures existing in distinct regions of a protoplanetary disk. Knowing what 3I Atlas is made of helps us reconstruct where around its parent star it most likely formed. Ground-based telescopes in turn contribute another vital dimension. While space telescopes circumvent atmospheric distortion and can observe wavelengths blocked by Earth's atmosphere, ground-based facilities offer their own unique advantages. They can be far larger, capable of gathering immense amounts of light. They can observe continuously for hours on end, and they are more easily upgraded and maintained. Observatories in Chile, strategically positioned at high altitudes, where the air is dry and stable, have been diligently tracking 3I Atlas nightly. They are meticulously measuring its light curve, the intricate pattern of how its brightness fluctuates over time. They are taking spectroscopic measurements, dissecting its light into component wavelengths to identify specific chemical signatures. They are vigilantly watching for any sudden changes, any unexpected outbursts, any deviations from its predicted behaviour. And here's where the scientific intrigue truly deepens. 3I Atlas is behaving mostly as expected, but not entirely. The overarching trend of increasing activity aligns with established comet models. Its composition appears consistent with known icy bodies. Its trajectory faithfully adheres to the laws of physics. However, the rate of its brightness increase exhibits moments that don't perfectly match the smooth curves predicted by standard models. There are subtle variations, minor anomalies, nuanced differences between what the equations suggest should happen and what the telescopes actually observe. Now, before any conclusions are hastily drawn, it's vital to understand that this is not entirely unusual. Real comets rarely conform to theoretical models with absolute perfection. They possess jets, specific regions on their surface that outgas more actively than others. They rotate constantly, altering which areas face the sun at any given time. They can have irregular shapes, porous surfaces, and internal layers with differing compositions. All these factors introduce variability, but scientists meticulously pay attention to all variation, because sometimes, rarely, but sometimes, it signifies something genuinely unexpected. Sometimes it is the first faint hint of a groundbreaking discovery. Most of the time, further more detailed analysis eventually reveals a mundane explanation, a rotation period that wasn't initially accounted for, a subtle, compositional gradient across the surface, or an outburst from a hidden pocket of volatile material that suddenly heated and released its contents. The very process of science involves diligently investigating these small mysteries, systematically ruling out explanations one by one until one is left with the most accurate and parsimonious answer. With 3i Atlas, that rigorous process is very much ongoing. The data continues to stream in. The analysis is continuously being refined, and December 19th will furnish the highest quality observations yet, potentially resolving some of these minor intriguing puzzles. One of the most ambitious aspects of this comprehensive observation campaign involves spacecraft that were not originally designed with 3i Atlas in mind, but which happen to be uniquely positioned to contribute invaluable data. The European Space Agency's JUICE mission, currently en route to Jupiter, carries instruments capable of observing the comet from a completely different vantage point than Earth-based telescopes. NASA's Stereo spacecraft, primarily designed to study the Sun, can observe 3i Atlas against the backdrop of solar activity, offering crucial context for how the solar wind interacts with the comet's tail. These opportunistic observations add critical perspectives that would be utterly impossible to obtain from Earth alone. They help us construct a three-dimensional picture of the object, rather than just a flat two-dimensional image. And then there's the Europa Clipper encounter, which deserves its own deeper discussion later, as it represents something truly extraordinary. A spacecraft that may have actually passed directly through the tail of an interstellar visitor, potentially collecting direct samples of material from another star system. But we will revisit that remarkable story. For now, let's focus on what the telescopes are telling us in real time. The coma surrounding 3i Atlas has expanded to encompass a region larger than Earth itself. This, however, is not unusual for active comets. The coma is incredibly diffuse, mostly empty space, with widely scattered molecules and dust particles. So its vast size does not imply a massive solid object. The nucleus, the actual solid body at the heart of the comet, is estimated to be several kilometers across. While not enormous by cometary standards, it is substantial enough to contain significant quantities of volatile ice, and large enough that its weak gravitational pull helps to briefly retain some material before it ultimately escapes into space. The tail, meanwhile, has extended for millions of kilometers, a faint ethereal streamer of material being gently pushed away by the solar wind, discernible only in long exposure images, but growing more prominent with each passing day. Spectroscopy has identified emission lines unequivocally consistent with several molecular species. Water, as expected, is prominent. Its signature appears strongly in both visible and infrared observations. Carbon compounds are also present, though pinpointing specific molecules requires meticulous analysis due to the overlapping spectral features of many carbon-based substances. There are also hints of silicate dust, rocky material intimately mixed with the ice now being released as the ice sublimates. This precise mixture of ice and rock is exactly what astronomers anticipate in comets. It's what we observe in comets originating from our own solar system, and it aligns perfectly with theoretical predictions of comet formation. On this front, 3i Atlas is checking all the boxes. But a crucial question scientists are grappling with is, why did the activity commence precisely when it did? Comets typically activate when they reach a certain critical distance from the Sun, when solar heating becomes intense enough to sublimate their surface ice. That specific distance varies depending on the comet's composition, as different types of ice sublimate at different temperatures. However, there are established ranges expectations built on thousands of previous comet observations. 3i Atlas began exhibiting activity right around the predicted distance, perhaps slightly earlier than some models suggested, but still well within the realm of normal. Yet the intensity of that activity, the sheer rapidity with which it ramped up, has left some researchers deeply intrigued. It's not that this phenomenon is impossible to explain through natural processes, it's that it demands very specific conditions, a particular type of surface composition or structure, to precisely match what has been observed. This is precisely the kind of intricate detail that keeps astronomers poring over data late into the night. It's not a contradiction that disproves anything, but rather a compelling puzzle, a pattern that urgently requires explanation. And the optimal time to gather the necessary data for that explanation is during the closest approach, when resolution is highest, when the light is brightest, and when instruments can make measurements simply impossible at greater distances. December 19th is that pivotal moment. Every telescope capable of observing 3i Atlas will be doing so around that date, diligently collecting as much information as physically possible, weather and technical issues permitting, before this fleeting opportunity inevitably fades. There's also the critical matter of the object's rotation. Most comets rotate tumbling through the void of space, and this rotation significantly influences how we observe them. Different parts of the surface periodically come into view, each potentially possessing distinct compositions or levels of activity. Determining the precise rotation period of 3i Atlas has proven challenging, primarily because the obscuring coma shrouds the nucleus, rendering direct observation of surface features impossible. However, subtle variations in brightness over time can provide vital clues about rotation, and preliminary analysis suggests a rotation period of several hours. This is typical, entirely normal, but confirming it definitively requires more data, more meticulous photometry, and more observations during the closest approach when these changes are most apparent. Scientists are also keenly watching for outbursts. Occasionally, comets experience sudden dramatic brightenings, not gradually but abruptly, when a hidden pocket of volatile material is suddenly exposed, or when a surface layer collapses, revealing fresh, pristine ice beneath. These outbursts are inherently unpredictable, impossible to forecast, yet incredibly fascinating to observe, because they offer rare glimpses into a comet's internal structure and composition. Should 3i Atlas undergo an outburst around December 19th, it would yield a treasure trove of additional data, a precious window into the layers beneath its surface. While not explicitly expected, it remains a distinct possibility, and astronomers will be poised and ready if it occurs. What is truly remarkable about this extensive observation campaign is its extraordinary level of coordination. Astronomy has always been an inherently international endeavour, but modern campaigns like this elevate that cooperation to unprecedented levels. Data is shared almost instantaneously. Researchers in different countries analyse the same observations from complementary angles, leveraging diverse expertise. Telescopes meticulously schedule their time to minimise gaps, ensuring continuous coverage. The result is a comprehensive, multifaceted picture painstakingly assembled from dozens of sources and refined by hundreds of scientists representing humanity's collective effort to understand this enigmatic visitor. It is science at its collaborative best, driven not by competition, but by a shared profound curiosity. The images we are seeing, the spectra we are painstakingly analysing, the measurements we are meticulously making. All of this builds toward December 19th, toward that specific date when proximity and alignment converge to create optimal conditions, toward that precise moment when we will achieve our clearest view, our most detailed data, our paramount chance to truly understand what 3i Atlas is. The telescopes are indeed seeing a comet, an active icy body releasing gas and dust as it responds to the sun's warming embrace. But they are also revealing subtle details that demand closer scrutiny, patterns that invite deeper questions, and a timeline that is inexorably counting down to a cosmic deadline. Let me now walk you through what will actually happen on that date, what its significance truly is, and why it represents both a magnificent climax and a poignant farewell. December 19th is not an arbitrary date, nor one chosen for dramatic effect or marketing. It is the precisely calculated moment when 3i Atlas achieves its closest point to Earth during this entire passage through our solar system. In astronomical parlance, this is termed close approach. The precision with which scientists can calculate this event is truly remarkable. They know not just the day, but the very hour, the very minute when the object will reach its minimum distance from us. This extraordinary calculation stems from meticulous trajectory tracking nightly measurements of the object's position, the application of sophisticated orbital mechanics, and careful accounting for gravitational influences. The mathematics are complex, but the outcome is certain. December 19th is the day. What does close approach actually signify? In everyday terms, it means 3i Atlas will be nearest to us when the vast distance between our planet and this interstellar visitor will be at its absolute smallest. That distance, however, is still enormous by human standards. We are talking about millions of kilometers. You will not be able to observe 3i Atlas with your naked eye, even at its closest approach, unless you possess exceptionally dark skies, keen vision, and an exact knowledge of where to look. It will appear as nothing more than a faint fuzzy star, and even that requires ideal conditions. But for telescopes for instruments engineered to gather light and magnify distant objects, December 19th represents the optimal window. Distance in astronomy is paramount. The closer an object, the brighter it appears, allowing more precious photons to reach our detectors. This in turn translates into superior resolution, enabling us to discern greater detail. Consider it this way. Imagine attempting to read text on a distant sign. From far away, you might discern its general shape, perhaps guess that it contains writing. As you approach, individual letters become legible, then words, then intricate details like font style punctuation, and even tiny imperfections in the printing. Distance dictates the depth of your observation. With 3i Atlas December 19th is the cosmic equivalent of getting close enough to read the fine print. Not literally, of course. We won't be seeing craters or surface features with the clarity we observe Mars or our Moon. However, we will obtain the highest quality spectroscopy, the sharpest images of the coma structure, and the most accurate measurements of brightness and composition we will ever achieve for this object. Here's a glimpse of what scientists ardently hope to observe on December 19th and in the days immediately surrounding it. First, highly detailed spectroscopy. By meticulously splitting the light from 3i Atlas into its component wavelengths with unprecedented precision, researchers can identify specific molecules and their relative abundances. Is water the dominant volatile, or are there substantial quantities of carbon monoxide or methane? Are complex organic molecules present? Are there unique isotopic ratios variations in the forms of elements that could offer profound insights into the temperature and conditions prevalent during its formation? These critical questions demand high signal-to-noise data, meaning an abundance of photons, a bright signal precisely what close approach so generously provides. Second, intricate coma structure imaging. The atmosphere surrounding a comet is never uniform. It exhibits jets where material streams outward from active regions on the surface. It possesses variations in density, sometimes forming concentric shells as pulses of material are released. By imaging the coma with high-resolution astronomers can meticulously map these structures, decipher the rotation of the nucleus pinpoint active regions, and model the rate of mass loss, how much material is being shed per unit of time. All of this narrative data tells a compelling story about the object's current state and its evolutionary journey. Third, tail dynamics. A comet's tail is not static. It dynamically responds to the solar wind, the relentless stream of charged particles emanating from the sun. It can exhibit ripples, dramatic disconnection events, where a section of the tail breaks away, and compositional variations along its immense length. By closely observing the tail, scientists gain invaluable insights into both the comet itself and the interplanetary environment it traverses. It serves as a natural laboratory for studying the complex interactions between solar wind and neutral gas and dust. Fourth, photometry for outburst detection. Continuous high-cadence monitoring of brightness can reveal sudden dramatic changes, those unpredictable outbursts that sometimes occur when fresh ice is unexpectedly exposed. If 3i Atlas undergoes a significant outburst around December 19th, telescopes will capture it, and rapid follow-up observations can then characterize its cause and what it reveals about the comet's interior composition. Amateur astronomers will also play a crucial unsung role. While they may not contribute to cutting-edge spectroscopy, their collective efforts in light curve monitoring are invaluable. Dozens, possibly hundreds of amateur observers across the globe will be tracking 3i Atlas with their personal telescopes, meticulously measuring its brightness and reporting their findings to shared databases that professional astronomers utilize to fill critical gaps in coverage. This citizen science contribution is immensely valuable, because professional telescopes operate under strict time constraints, weather limitations, and potential technical issues. Amateurs provide crucial redundancy and continuity, and for those participating, it is a rare opportunity to be an active part of a historic observation, to contribute tangible data to the study of an interstellar visitor. Will you personally be able to see it? From a dark location far removed from city lights with a decent pair of binoculars or a small telescope? Yes, probably. 3i Atlas will likely be visible as a faint smudge, a fuzzy patch of light that differentiates itself from a star due to its extended nebulous coma. It will not be a spectacular blazing sight, nor will it resemble the iconic comet photographs you've seen, with immense sweeping tails across the sky. Those images typically require either exceptionally bright comets or long exposure astrophotography. But if you know precisely where to aim your instrument guided by a star chart or a smartphone app, you can find it. You can gaze upon it with your own eyes filtered through glass and mirrors, and know that you are witnessing photons that have travelled billions of miles from an object that originated around another star. That profound connection alone is worth stepping outside on a crisp December night. For those unable to observe personally, a wealth of images will become available. Professional observatories often release their data publicly, sometimes within days. Space telescope observations are eventually archived and made accessible. Striking photography from dedicated astrophotographers, individuals who spend hours capturing and processing celestial images, will undoubtedly appear online. You will be able to witness what 3i Atlas looks like at its closest approach, even if you are nowhere near a telescope. The internet has democratized astronomy, transforming distant observations into shared global experiences. But let's be absolutely clear about what will not happen on December 19th, for misconceptions often arise around such events. There will be no visible change to the night sky for casual observers. You will not look up and perceive a bright new object dominating the heavens. There will be no impact, no near miss, no danger whatsoever. The distance at closest approach, while minimal for this event, is still inherently safe by any measure millions of kilometers. Space is vast beyond comprehension. Even close approach, in astronomical terms, is distant by human standards. There will be no measurable gravitational effects on Earth, no altered tides, no tremors, no atmospheric changes. The object is far too small and far too distant to exert any discernible influence on our planet. What will happen is intensive data collection, rigorous documentation, and profound study. Scientists will work through the night at observatories, executing intricate observation schedules, meticulously checking instrument functionality, ensuring every possible minute of clear weather is used productively. Researchers will analyze incoming data, running it through sophisticated software pipelines, identifying intriguing features, and flagging anything unexpected for closer scrutiny. This is not a Hollywood spectacle. It is not dramatic in a cinematic sense, but it is profoundly thrilling for those involved. For its discovery unfolding in real time, the arduous yet exhilarating process of learning something humanity did not know before, and it is finite. That is the true weight of December 19th. After this date, 3I Atlas will continue its trajectory away from the Sun, accelerating as it goes steadily dimming from our perspective as the distance rapidly increases. Every day after the 19th observations will become more challenging. The signal will weaken. Intricate details visible during close approach will fade below detection limits. Within weeks, only the largest telescopes will be able to track it. Within months, it will vanish from our view entirely, a fading point of light dissolving into the cosmic background lost to observation, but forever enshrined in our memory and data archives. Scientists are acutely aware of this. They feel the immense pressure of that deadline. This is why the observation campaign is so intensely coordinated, why so many resources are being dedicated to this single object, why December 19th has been circled on calendars and marked in scheduling systems across dozens of institutions. You get one chance, one fleeting window, one optimal opportunity to gather the best data you will ever obtain. After that, the object transforms into a data set, a collection of measurements and images to be analysed and reanalyzed for years to come, but never again observed with such clarity. There's something profoundly poignant in that finality, something that echoes the human experience itself. We encounter moments, people and phenomena that we inherently know are temporary, that will eventually pass, and that very knowledge compels us to pay attention, to be present, to appreciate what we have while we still have it. For astronomers studying 3I Atlas, December 19th is precisely that moment. It's not just a date, it's a culmination, a peak, the pinnacle of our opportunity to understand a visitor that traversed unimaginable distances and will soon return to that distance, never to be seen again by anyone currently alive. So when December 19th arrives, when that moment of closest approach has passed, we will possess whatever data was meticulously gathered, whatever observations were physically possible, whatever the weather allowed and the instruments captured. And from that finite, precious set of information, scientists will painstakingly extract understanding. They will write papers, propose new theories, and engage in robust debates about interpretations. Some questions will be definitively answered. Others will remain open, lingering as tantalizing mysteries. And in that rich mixture of knowledge and enigma, we will discover the true value of this event. Not that it reveals everything, but that it reveals something profound. Something tangible about the universe beyond our solar system, something concrete about how comets form around other stars, something meaningful about the vast, elegant processes that govern planetary systems throughout our galaxy. But before we fully embrace this date as simply a scientific milestone, we must confront the vibrant debate that swirls around it. Because while most astronomers perceive December 19th as an opportunity to study a natural comet, one prominent scientist views it as potentially something far more significant, something that challenges our deepest assumptions about what we're truly observing and what might be possible. That is where we turn next to the hypothesis that has ignited both controversy and conversation in equal measure, to the idea that 3I Atlas might not be entirely what it seems. Dr. Avi Loeb is not a fringe figure. This is a critical point to establish up front. His hypothesis regarding 3I Atlas is unconventional enough that it would be easy to dismiss as originating from someone outside the scientific mainstream. Yet Loeb is thoroughly ingrained within the mainstream of professional astronomy. He is the former chair of Harvard University's astronomy department, one of the most prestigious positions in the field. He has authored hundreds of papers in peer-reviewed journals and contributed to projects ranging from black holes to the early universe to exoplanets. His credentials are, in a word, impeccable. His reputation until recently was that of a highly respected theoretical astrophysicist, tackling conventional problems with rigorous established methods. So when an individual with such formidable credentials suggests that an interstellar object might be artificial, that it could potentially be a probe or even a mothership dispatched by an extraterrestrial civilization, people pay attention. Not necessarily with agreement nor with universal acceptance, but with an undeniable sense of intrigue. Because Loeb is not making this claim lightly. He is not building it upon wild speculation, nor is he disregarding the scientific method. What he is doing is asking a question that makes many of his colleagues distinctly uncomfortable. Have we truly considered all possibilities, or are we prematurely ruling out explanations simply because they seem unlikely or unsettling? The mothership hypothesis, as it has come to be known, centres on the idea that some interstellar objects might be more than mere natural debris from other star systems. They might be intentional artificial constructs designed and deployed either as reconnaissance probes exploring the galaxy, or as larger motherships carrying smaller craft tasked with investigating specific planetary systems. Loeb famously applied this thinking to Oumuamua, arguing that its anomalous shape, its unexplained acceleration, and its puzzling lack of visible outgassing could be consistent with a light sail, a thin reflective structure propelled by starlight. That suggestion sparked an enormous debate with most astronomers, ultimately concluding that natural explanations, while requiring some unusual conditions, still provided a better fit for the data than invoking alien technology. Now with 3i Atlas, Loeb is raising similar questions. Again, he's not claiming certainty or asserting proof. Instead, he's asking if we should at the very least consider this possibility before definitively labelling the object as a natural comet and moving on. His argument rests on several key points, and to evaluate them fairly, we must understand precisely what he is saying, rather than simplified caricatures. First, Loeb points to specific patterns in 3i Atlas's activity, the way it brightened, the timing of its coma's appearance, and the intensity of its outgassing. He notes that these don't perfectly align with typical comet models. While they can certainly be explained by natural processes, such explanations often require specific, sometimes unique assumptions about composition and internal structure. Loeb poses, if we approach this object without a predisposition to assume naturalness, if we were completely objective, would we not consider other possibilities? Would we not ask if its activity could be controlled rather than purely thermal? If its trajectory could have been influenced by something beyond gravity and random outgassing? Second, he emphasises the profound opportunity this object represents. If extraterrestrial civilizations exist, and if they are exploring the galaxy in ways analogous to how we're beginning to explore our own solar system, then interstellar space should contain their probes. Perhaps not many given the galaxy's immense scale, but certainly not zero. And these probes would traverse the space between stars just as natural objects do, appearing in our skies with similar trajectories. The only way to differentiate an artificial object from a natural one is through meticulous, detailed study, specifically looking for anomalies for behaviours that defy natural explanations. Loeb contends that we should be doing this systematically, rather than presuming naturalness by default. Third, he elaborates on the concept of a mothership, particularly in relation to objects that might release smaller probes as they traverse star systems. The hypothesis suggests that a large kilometre-scale object could potentially carry numerous smaller craft, each designed to investigate planets or moons within the systems it encounters. As the mothership approaches a star, it might deploy these smaller craft, which would then manoeuvre independently. From a distance, observing only the larger object, we might perceive increased activity, a release of material or subtle changes in trajectory, all of which could be mistakenly interpreted as conventional cometary behaviour, when in fact it represents the deployment of smaller intelligent vehicles. It is crucial to grasp that Loeb is not claiming 3i Atlas is definitively artificial. He is not asserting that the mothership hypothesis is proven, or even highly probable. His core argument is that it is testable. He suggests that December 19th offers a unique opportunity to actively search for signatures that could differentiate between a natural and an artificial origin. He believes we should be designing our observations specifically to rule out artificiality, rather than simply assuming it away. He implores the scientific community to seriously consider the question of whether we are alone not merely as a philosophical exercise, but as a legitimate, actionable observational program. What then would artificial look like? According to Loeb, one would search for several distinct signatures, anomalous acceleration that cannot be fully explained by outgassing or gravitational forces, the presence of structured objects within the coma that maintain coherence rather than dispersing randomly, radio emissions or other electromagnetic signals that do not align with natural processes, geometric shapes or discernible regularities in the distribution of material, or trajectory changes that strongly suggest purposeful propulsion. None of these are straightforward to detect, and it's important to acknowledge that natural phenomena can sometimes mimic artificial signatures. However, the crux of Loeb's argument is the imperative to deliberately look to treat the question as scientifically legitimate rather than dismissing it out of hand. The reason this hypothesis often generates such intense controversy is not due to any lack of credentials on Loeb's part, nor because the idea of extraterrestrial technology is inherently unscientific. Science is perfectly capable of exploring such questions. The controversy primarily stems from differing priors, from how scientists weigh probabilities. In Bayesian terms, most astronomers assign an extremely low prior probability to artificial objects. Not zero, but exceedingly small. They firmly believe that natural explanations must be exhausted, first that extraordinary claims demand extraordinary evidence, and that invoking alien technology is a step one should only take when literally nothing else fits the observed data. Loeb counters that this deeply ingrained approach can inadvertently bias researchers against recognizing genuinely anomalous objects. If one consistently assumes naturalness, one might tragically overlook the singular instance where that assumption does not apply. This is, in essence, a philosophical as well as a scientific debate. How open-minded should we be to unconventional explanations? At what precise point does open-mindedness become credulity? How do we judiciously balance rigorous skepticism with boundless curiosity? These are not questions with facile answers, and entirely reasonable scientists hold differing opinions. What makes Loeb's contributions particularly interesting is that he has effectively forced this conversation. Regardless of whether one agrees with him or whether one finds the mothership hypothesis compelling or far-fetched, he has made it impossible to completely ignore the question. He has prominently placed the possibility on the table, and in doing so he has ensured that at least some observations of 3i Atlas will be specifically designed to test it. There is also crucial context regarding Loeb's broader scientific project. He has founded and championed initiatives specifically aimed at searching for techno-signatures, definitive evidence of extraterrestrial technology. He firmly believes this is a legitimate and profoundly important scientific endeavour that has been historically underfunded and underexplored relative to its immense significance. Some of his colleagues view this as a valuable pursuit, actively pushing the field in necessary forward-thinking directions. Others, however, perceive it as attention-seeking, as an emphasis on spectacle over substantive scientific inquiry. That inherent tension inevitably colours reactions to the mothership hypothesis. Is Loeb acting as a provocative yet serious scientist asking essential uncomfortable questions, or is he overstating possibilities to generate heightened interest in his projects? Different individuals answer this question differently, often depending on their personal perspective and professional relationship with him. From a purely logical standpoint, the mothership hypothesis is not inherently absurd. If technological civilizations are indeed common throughout the cosmos, and if they have persisted for sufficiently long periods, then the galaxy should contain their artifacts. Probes launched millions of years ago might still be functional, passively drifting through space, occasionally passing through systems like ours. The fundamental challenge, however, is that we possess absolutely no empirical data on how common such civilizations truly are, how long they typically endure their motivation for exploration, or the methods they might employ. Without that crucial data, any prior probability we assign is essentially an educated guess, albeit one dressed in mathematical equations. We simply do not know if intelligent life is exceedingly rare or remarkably common. We do not know if technological species typically self-destruct or explore for eons. We are reasoning from a sample size of one ourselves. What we can do, however, is rigorously test. We can meticulously examine objects like 3i Atlas and ask, does this object exhibit any unambiguous signs of artificiality? And if the answer is unequivocally no, if every observation is entirely consistent with natural processes, then we update our understanding. We conclude that this specific object is natural, and we patiently await the next interstellar visitor to pose the question anew. That is the methodical, incremental way science progresses on questions where theoretical frameworks are underdeveloped and empirical data remains sparse. One test case by case, systematically ruling out possibilities and progressively narrowing down explanations. The emotional response to Loeb's hypothesis is also worth examining. Many scientists experience frustration with it, feeling that it often diverts crucial attention and resources from the profound and painstaking scientific work of understanding comets and interstellar objects in their natural forms. They express concern that media coverage disproportionately focuses on the sensational possibility of alien probes, rather than the fascinating yet less headline-grabbing reality of natural cosmic processes. They worry that the public will misunderstand, believing that astronomers widely endorse the idea that 3I Atlas is a spaceship, when in fact the vast majority do not. There's a protective instinct at play here, a fervent desire to manage public perception and avoid any association with pseudoscience. However, there is another equally valid emotional response: excitement. Some individuals, including certain scientists, find Loeb's willingness to ask unconventional questions profoundly refreshing. They appreciate his challenge to orthodoxy, his questioning of deeply held assumptions, and his courage in pushing established boundaries. They may not necessarily agree with his conclusions, but they deeply value the spirit of inquiry, the steadfast refusal to accept comfortable answers without rigorous scrutiny. For them, the mothership hypothesis represents excellent science precisely because it is testable, falsifiable, and provocatively productive. So where does this leave us with December 19th? It means that the crucial observations made during close approach will be analysed through multiple distinct lenses. Most astronomers will be meticulously searching for data pertaining to cometary processes, to composition and structure, and to activity patterns, all the questions that build our fundamental understanding of how comets form and evolve. However, some inspired or challenged by Loeb's hypothesis will also be keenly looking for anomalies, for anything that defies expectations, for signals that might indicate something beyond a purely natural object. And this diverse approach is healthy. It is how one mitigates confirmation bias, by having various perspectives critically examining the same data, by allowing for robust disagreement and vibrant debate. The mothership hypothesis is highly unlikely to be definitively proven on December 19th. That would require truly extraordinary evidence, unambiguous, undeniable signs of artificiality that cannot be explained by any other means. What is far more probable is that the data will powerfully reinforce the natural comet explanation, demonstrating that everything we observe is entirely consistent with known physics and chemistry, thus largely closing off many of the ambiguities that currently allow room for speculation. Even that outcome, however, is immensely valuable. It is valuable to rigorously test unconventional ideas and find them wanting. That is how we build greater confidence in conventional explanations. That is how we ensure we are not overlooking something profoundly important. And if against all prevailing expectations something truly anomalous does appear, if the observations reveal something that cannot be easily explained, something that strongly suggests intelligence, design, or purposeful construction, then everything changes. Then the December 19th event would transform from a mere scientific milestone into a civilizational one. Then we would confront implications far beyond the realm of astronomy, questions about our fundamental place in the universe, the prevalence of intelligence, and the tantalizing possibility of contact. This seems highly unlikely. Most scientists would wager heavily against it. But unlikely is not impossible, and the only true way to know is to look. So the mothership hypothesis subtly hangs over December 19th as a possibility, however remote, that imbues the observations with an additional layer of significance. It transforms the event into not just a study of a comet, but a test of our collective openness to unexpected discoveries. It challenges us to approach the incoming data with both rigorous scientific precision and expansive imagination, with healthy skepticism and profound curiosity, with the understanding that nature typically follows expected patterns, but occasionally breathtakingly surprises us. Whether you find the hypothesis compelling or misguided, it has undeniably achieved one critical outcome. It has compelled the scientific community to think more deeply and carefully about what they are observing and why they interpret it the way they do. And that profound reflection that rigorous examination of fundamental assumptions is never wasted effort. Let's now turn to the robust response from the mainstream scientific community, how they directly address Loeb's claims, and why they remain confident that 3i Atlas is precisely what it appears to be, a natural visitor from another star system. The astronomical community has responded to Loeb's mothership hypothesis not with outright dismissal, but with detailed evidence-based counter-arguments. This distinction is critical as it demonstrates that the debate, while sometimes contentious, is firmly unfolding within the established bounds of scientific discourse. Scientists are not simply ignoring Loeb's claims, they are meticulously addressing them point by point, illustrating why natural explanations remain far more convincing given the totality of available evidence. Understanding these rebuttals is key to comprehending why the vast majority of researchers studying 3i Atlas believe we are observing a comet and nothing more. The most fundamental starting point is composition. Spectroscopic analysis of 3i Atlas consistently reveals emission lines indicative of water vapour, various carbon compounds and silicate dust. These are precisely the materials one would expect to find in a comet. They constitute the very building blocks of comets within our own solar system. They are what theory unequivocally predicts should form in the frigid outer regions of protoplanetary disks, where temperatures are sufficiently cold for ices to condense. If 3i Atlas were in fact an artificial object, a manufactured construct, one would then be compelled to explain why it is releasing these specific natural materials. One would have to propose that the artificial object is either cunningly disguised to mimic natural phenomena, or that it inexplicably carries these substances for some unknown purpose. Both possibilities introduce layers of complex assumptions that natural explanations simply do not require. Next, consider the observed activity patterns. Yes, 3i Atlas's brightness increase does exhibit some features that do not perfectly align with overly simplistic comet models. However, when one accounts for the realistic properties of comets, their irregular shapes, non-uniform surface compositions, and rotation that exposes different areas to sunlight at varying times, those subtle features become entirely explicable. Comets are not perfect, smooth spheres with homogeneous surfaces. They are rather loosely bound rubble piles of ice and rock held together by weak gravity. They possess distinct regions that outgas more actively, creating dynamic jets that switch on and off as the surface rotates. There are areas where insulating layers of dust accumulate only to suddenly break away. All of these factors inherently introduce variability in brightness and activity that simple models cannot fully capture, but which more sophisticated, nuanced models can readily account for. Researchers have consistently highlighted that every anomaly Loeb points to can be elegantly addressed within the framework of conventional comet physics. The timing of when its activity commenced, consistent with solar heating reaching the sublimation temperature of its surface ices given the object's distance and composition. The rate of brightening, well within the observed range of other comets, once rotation and surface heterogeneity are considered. The spectral features, a precise match for known cometary compounds. There is quite simply no need to invoke anything beyond well-understood physical processes. And in the scientific method, when two explanations equally fit the observed data, one invariably prefers the explanation that requires fewer assumptions, the one that builds upon established knowledge rather than proposing entirely new phenomena. That, in essence, is Occam's razor, a guiding principle, not because simpler explanations are always correct, but because they are correct far more often than not. The trajectory of 3i Atlas is another pivotal point. It follows a distinct hyperbolic path through our solar system, a trajectory perfectly consistent with an interstellar object influenced solely by the Sun's gravity and the small, well-understood thrust from its outgassing the aforementioned rocket effect. This trajectory can be calculated with astonishing precision, using Newton's laws and principles of general relativity, and it matches all predictions. There are no unexplained course corrections, no sudden manoeuvres that would even remotely suggest purposeful propulsion. If this were an artificial object capable of actively adjusting its path, one would unequivocally expect to observe detectable deviations from a purely gravitational orbit. We do not. The path is clean, predictable, and entirely natural. Then there's the fundamental question of why an artificial object would behave in such a manner. If an advanced civilization were to dispatch a probe to meticulously investigate a star system, why would it merely pass through on a hyperbolic trajectory? Why not execute a maneuver to enter a bound orbit, enabling it to study the system in exquisite detail for an extended period? Why not adjust its course to visit potentially interesting targets like Earth or Jupiter? The observed trajectory of 3I Atlas simply makes no sense as an intentional pattern of exploration. It makes perfect unambiguous sense as a randomly ejected comet from another system happening to pass through ours, purely due to the random geometry of its original ejection and our relative motion through the vast galaxy. Critics of the mothership hypothesis also frequently emphasize the critical issue of prior probability. We unequivocally know that comets exist. We know that planetary systems coalesce around other stars. We know that gravitational interactions can and do eject objects into interstellar space. All of these are confirmed facts. We possess direct empirical evidence for each sequential step in the natural process that creates an object like 3I Atlas. What we do not possess is any confirmed evidence of extraterrestrial technology. We do not know if intelligent life is common. We do not know if technological civilizations routinely dispatch probes. We do not know if such probes would deliberately resemble comets. We are in essence layering unknowns upon unknowns. When one objectively compares the probability of a natural comet versus an artificial probe given what we actually know about the universe, the natural explanation wins by a substantial undeniable margin. This is not to say that scientists are entirely closed to the monumental possibility of artificial objects. Indeed, many would be absolutely thrilled to discover definitive evidence of extraterrestrial technology. It would undeniably be the discovery of the century, perhaps even of all human history. But extraordinary claims demand extraordinary evidence, and thus far 3I Atlas presents no evidence that cannot be comprehensively explained by natural processes. The standard for claiming artificiality must by necessity be exceedingly high, precisely because the implications are so utterly profound. One needs something unambiguously clear, something that unequivocally indicates design or intelligence, something that natural processes simply cannot account for. Spectral lines matching natural compounds do not meet that stringent standard. Variable brightness does not meet it. A hyperbolic trajectory does not meet it. There's also a deeply practical aspect to the scientific rebuttal. Astronomers who are meticulously studying 3I Atlas have specific, well-defined scientific goals related to understanding cometary composition, the conditions of the interstellar medium, and the intricate processes of planetary system formation around other stars. Focusing excessively on the mothership hypothesis, they argue detracts from these fundamental goals, diverting precious attention and finite resources toward questions that currently lack substantive supporting evidence. It is not that these questions are forbidden, it is that they are unproductive given the empirical data we are actually observing. If clear, undeniable anomalies were to emerge, if something genuinely inexplicable presented itself, then unequivocally the focus would shift and an intense investigation would commence. But in the absence of such compelling anomalies, the scientific community prioritizes studying what is demonstrably there, a comet. Some researchers have openly expressed frustration that Loeb's public advocacy for considering artificial explanations inadvertently creates misperceptions. Media coverage, they note, often sensationalizes the most dramatic angle, meaning articles about 3i Atlas disproportionately mention the mothership hypothesis, despite it being a pronounced minority view within the scientific community. This can lead the public to mistakenly believe there is more widespread scientific debate about artificiality than truly exists. Surveys of astronomers actively working on interstellar objects reveal that the vast majority consider 3i Atlas to be a natural object with very high confidence. The real scientific conversation, they argue, centres not on whether it's natural, but on the intricate details of its specific composition and its unique formation environment. The nuanced substantive discussion sometimes gets regrettably overshadowed, yet despite this understandable frustration, the rebuttals from the mainstream remain substantive and respectful, rather than dismissive or personal. Academic papers addressing Loeb's claims do not attack him personally or question his competence. Instead, they rigorously engage with his arguments, systematically demonstrate why natural explanations are sufficient, and propose specific observations that could definitively distinguish between competing hypotheses. This is science functioning precisely as it should, disagreements handled through evidence and reasoned argument, rather than by appeals to authority or inflammatory rhetoric. Even those who strongly disagree with Loeb's conclusions respect the fundamental process of testing ideas against empirical data. What then would it take to change minds? What specific observation or measurement would truly convince mainstream astronomers that 3i Atlas is in fact artificial? The answers are quite clear. The unequivocal detection of radio signals or other electromagnetic emissions that clearly carry information or exhibit modulation patterns demonstrably inconsistent with natural processes. The unambiguous observation of objects visibly separating from 3i Atlas in controlled ways, maintaining formation or executing deliberate maneuvers. The discovery of materials or structures with properties that do not occur naturally, such as pure refined metals or complex geometric arrangements. Or sudden inexplicable changes in trajectory that cannot be accounted for by outgassing or any other known natural forces. Any of these would be taken with the utmost seriousness, immediately triggering intense collaborative follow-up investigations. The scientific bar is necessarily high, but it is not arbitrary. It is set at a level required to rigorously avoid false positives, while remaining genuinely open to groundbreaking discoveries. As December 19th draws closer, both perspectives will be scrutinizing the same incoming data. Mainstream scientists will be meticulously searching for intricate details about ice composition, dust properties, and activity mechanisms, all the crucial questions that meticulously build our understanding of how comets form and evolve. Those sympathetic to Loeb's approach, however, will be actively searching for anomalies, for anything unexpected, for signals that might subtly indicate something beyond purely natural processes. And this duality is perfectly acceptable. It is in fact healthy for scientific progress. Different expectations often lead to different analytical pathways, and sometimes the unexpected analysis reveals something that the conventional approach might have overlooked. The scientific method is inherently designed to accommodate this kind of disagreement. One makes predictions, one meticulously gathers data, one rigorously compares observations to those predictions. Hypotheses that align with the data survive, those that do not are modified or discarded. Over time, through countless observations and tests, a robust consensus emerges around explanations that consistently prove reliable. With 3i Atlas, the natural comet hypothesis has thus far survived every rigorous test. It accurately predicts what we observe. It explains the incoming data without having to invoke unknown phenomena. It connects this specific object to a broader, deeper understanding of planetary systems and the vastness of interstellar space. That is why it remains the dominant view. But dominance does not equate to absolute certainty. Science is always provisional, always inherently open to revision. if compelling new evidence unequivocally demands it. The astronomers who confidently assert that Three-Eye Atlas is natural would, if confronted with truly compelling evidence of artificiality, promptly adjust their views. That is not weakness. That is the intrinsic strength and integrity of the scientific approach. One follows the evidence wherever it leads, even if it leads somewhere utterly unexpected. As of now, the overwhelming evidence leads to a comet, a fascinating, immensely valuable, scientifically rich comet from another star system, carrying vital information about processes far beyond our own solar system, but a comet nonetheless. So as we move toward December 19th with these two fundamental frameworks, natural versus potentially artificial, we do so knowing that one is strongly, overwhelmingly supported by current evidence and scientific consensus, while the other remains a speculative possibility certainly worth testing, but not yet supported by empirical data. The upcoming observations will in all likelihood reinforce the natural explanation. They will add invaluable detail and nuance to our understanding of comets, and will definitively answer specific questions about Three-Eye Atlas's composition and behaviour. Whether they also fully address Loeb's concerns, whether they provide the kind of exhaustive, detailed scrutiny that definitively rules out artificiality to his satisfaction remains to be seen. But either way, the data will be publicly accessible, the analysis will be transparent, and the scientific process will rigorously continue. What truly matters now is not winning a debate, but learning what this silent visitor can truly teach us about the magnificent galaxy we inhabit. Let's now explore what realistic scenarios could unfold on December 19th, and beyond what genuine surprises might await us, and crucially what dangers definitely do not exist despite any anxieties some people might understandably feel. Let's address the anxiety first because I understand it exists. Whenever a celestial object makes a close approach to Earth, whenever there is significant media coverage of an astronomical event, some individuals inevitably harbour concerns. They envision catastrophic scenarios, threats to our planet, or consequences far beyond mere scientific interest. So before we delve into what could realistically happen on December 19th, let's be absolutely unequivocal about what cannot happen. The Three-Eye Atlas poses no danger to Earth. None. Zero. The distance at its closest approach, while the minimum it will reach, is still astronomically enormous, millions of kilometres. There is absolutely no possibility of collision, no chance of impact, no risk whatsoever to satellites, spacecraft or anything within Earth's vicinity. The object isn't even coming remotely close to the Moon. It is not entering Earth's sphere of gravitational influence in any meaningful way. If you are watching this with any level of concern about safety, please let that concern go. This event is profoundly scientifically exciting, but it is unequivocally non-threatening. With that critical clarification made, let's discuss what actually could happen, encompassing both the expected and the tantalizingly possible surprises. The most probable scenario is that December 19th will unfold with scientists successfully gathering an abundance of excellent data further confirming Three-Eye Atlas as a natural comet, precisely measuring its composition and significantly augmenting our existing knowledge of interstellar objects. Telescopes will capture exquisitely sharp images of the coma's intricate structure. Spectrometers will precisely identify molecular abundances. Photometry will meticulously track brightness changes. All of this rich data will subsequently feed into scientific papers and in-depth analyses that will emerge over the ensuing months, collectively building a comprehensive, detailed picture of this remarkable visitor. That is the expected outcome, and it is immensely valuable even if it lacks Hollywood drama. However, comets by their very nature can be unpredictable. They possess a capacity to surprise us. One distinct possibility is an outburst. A sudden dramatic increase in brightness occurring as fresh ice is abruptly exposed or as a structural feature on its surface collapses. Outbursts happen relatively frequently in comets, not with absolute predictability, but often enough that catching one during an intensive observation campaign like this is certainly plausible. If 3i Atlas undergoes a major outburst around December 19th, it would brighten significantly, potentially becoming visible to the naked eye for a brief period under ideal conditions. More importantly, it would offer scientists a rare, invaluable glimpse at interior material at layers beneath the surface that are normally obscured. The composition of that newly exposed material could differ significantly from the surface composition, potentially revealing a deeper history of the object's formation and subsequent evolution. Outbursts also create unparalleled opportunities for studying dynamic processes. When material is suddenly released, it generates rapidly evolving structures in the coma and tail that change over mere hours and days. Witnessing that evolution in real time provides profound insights into how gas and dust interact, how the solar wind affects them, and how the object's rotation influences the distribution of this released material. High-cadence observations taking images or spectra repeatedly over very short intervals can capture this intricate process in exquisite detail. Several observatories have specifically planned for this type of monitoring around December 19th, poised to rapidly increase observation frequency if activity noticeably intensifies. Another possibility involves trajectory refinement. While the overall path of 3i Atlas is already well established, outgassing inherently creates small, non-gravitational forces that can subtly alter its trajectory. These accelerations are common in comets, but their precise magnitude depends on the location of active regions on the surface and the object's rotation. More precise measurements during close approach will significantly refine our understanding of these forces, allowing for even more accurate predictions of 3i Atlas's future position as it departs our solar system. That level of precision is crucial for coordinating future observations, for knowing exactly when the object will be in favourable positions for different telescopes. There's also the tantalising chance of detecting something genuinely unexpected in its composition. Most scientists anticipate 3i Atlas to exhibit the typical cometary mixture: water ice carbon, monoxide, carbon dioxide, methane, ammonia, alongside rocky dust and perhaps some complex organic molecules. But what if there's something truly unusual? What if isotopic ratios are significantly different from those found in solar system comets, suggesting formation in an environment with distinctly different temperatures or chemical precursors? What if entirely new molecules, compounds that formed under conditions not prevalent in our own solar system, are detected? Such discoveries would not render 3i Atlas artificial, but they would be profoundly scientifically fascinating, compelling us to expand and revise our models of what planetary systems can produce. Regarding the mothership hypothesis, December 19th is undeniably the moment when any unambiguous signs of artificiality would be most likely to emerge. If there are any hidden structures, artificial signals, or intelligent behaviours, this is when our instruments are optimally positioned to detect them. Dr. Loeb and those sympathetic to his views will be actively searching for such anomalies. Emissions at unusual wavelengths, discernible geometric patterns within the coma, or course corrections that defy explanation by natural outgassing. The probability that such evidence will appear remains low based on everything we've observed so far. However, the possibility, however remote, still exists. And if it does appear, if there's undeniable, unambiguous evidence of artificiality, then we are truly in uncharted territory. Then the conversation would pivot dramatically from astronomy to astrobiology, to policy, to philosophy. Then December 19th would become a date that fundamentally transforms human civilization's understanding of its place in the universe. More realistically, the observations will overwhelmingly strengthen the natural comet hypothesis, while potentially leaving a few minor ambiguities unresolved. This is a common occurrence in science. One rarely obtains perfect data that definitively answers every single question. More often, one acquires data that robustly supports one interpretation, renders others highly unlikely, but does not entirely eliminate every conceivable alternative. With 3i Atlas, we will likely conclude with very high confidence that it is a natural object possessing a detailed understanding of its composition and behaviour, yet perhaps retaining one or two small mysteries that await future analysis or the arrival of subsequent interstellar visitors to help resolve. There's also the practical reality of observational challenges. Weather is inherently unpredictable. Telescopes can experience technical issues. Not every planned observation will succeed perfectly. Some facilities might lose critical nights to clouds or equipment malfunction. That is the unavoidable reality of observational astronomy. One plans for redundancy coordinates across multiple sites and hopes that enough observations succeed to construct a complete picture, even if individual attempts fail. The global nature of this campaign significantly helps here. If one observatory is clouded out, another on a different continent might have clear skies. If one instrument malfunctions, others can partially compensate. Amateur astronomers further contribute to this resilience. While they cannot perform cutting-edge spectroscopy or capture the high-resolution images that professional instruments can, they can meticulously monitor brightness, track position, and report sudden changes. If 3i Atlas brightens dramatically due to an outburst, amateurs might be the first to notice simply because they often observe more frequently than scheduled professional observations. That critical information is then rapidly shared through dedicated networks and alert systems, allowing professionals to quickly respond, redirecting their telescopes to capture the event while it is still actively unfolding. What about after December 19th? The event is far from over once the closest approach has passed. It is in fact the beginning of a new phase. As 3i Atlas moves away from both Earth and the Sun, it will continue to be observable for weeks, then months, albeit with gradually declining visibility. Scientists will track it for as long as humanly possible, meticulously observing how its activity changes as solar heating diminishes how its coma evolves and how quickly the object fades. This extended observation period provides crucial context for the close approach data, illustrating how the peak activity relates to the object's longer-term behaviour. Eventually 3i Atlas will become too faint to observe with most telescopes. Only the very largest instruments will be able to track it, and even they will ultimately lose sight of it as the distance steadily increases. There will be a final observation, a last image or spectrum, the last photons from this visitor that will ever reach our detectors. That precise moment will not be announced in real time. It will be recognised retrospectively when persistent attempts to observe the object consistently fail, when it's simply no longer bright enough to detect against the pervasive background noise of space. And then 3i Atlas will become history, a completed observation, a finished chapter in the ongoing study of interstellar objects. But the data lives on. Every image, every spectrum, every measurement is meticulously archived, available for researchers to analyse and reanalyse for decades to come. Questions we don't even know to ask yet might be answered by this very data in the future, when new techniques or theories eventually emerge. That is the enduring, priceless value of thorough observation campaigns. They create scientific resources that serve discovery long after the event itself has concluded. For those of us watching from the sidelines, not operating telescopes, or analysing spectra, December 19th and its surrounding days offer something profoundly different, a shared moment of cosmic attention. A time when people across the globe are gazing at the same object, contemplating the same questions, and curious about the same outcomes. In an era often characterised by division and fragmentation, there is something deeply unifying about humanity collectively looking up together, wondering about the same visitor from beyond. It serves as a powerful reminder that we're all on this planet together, sharing the same sky, part of the same grand story of exploration and discovery. What could go wrong? Practically nothing of consequence. Scientifically, the only genuinely wrong outcome would be widespread equipment failures or severe weather that prevents crucial observations. But even that is significantly mitigated by the built-in redundancy of a global campaign. What could go right? We could learn the precise composition of this object, definitively confirm or refine our theories about planetary system formation. gain a deeper understanding of how interstellar space impacts objects traversing it, and add a third intricately detailed case study to our burgeoning knowledge of interstellar visitors. We could, though less likely, detect something utterly unexpected that expands our fundamental understanding of chemistry or physics. And we could, though very unlikely, but not impossible, find undeniable evidence that we're not alone in the universe. These potential outcomes span from immensely valuable to utterly transformative, regardless of which unfolds. December 19th represents unequivocal progress. It represents humanity deploying its finest technology and intellect to comprehend the cosmos a little better, and that in itself is worth celebrating, irrespective of the specific discoveries that ultimately emerge. Before we conclude this extensive exploration, however, there is one more crucial piece of the story that deserves significant attention, something that has already occurred but has not received the widespread coverage it so merits: a spacecraft encounter that might have provided humanity's most direct contact yet with material originating from another star system. Here is something truly remarkable that for various reasons hasn't yet made headlines in the way it should. In late October or early November of this year, NASA's Europa Clipper spacecraft, currently on its monumental journey to Jupiter, likely passed directly through the ion tail of 3I Atlas. Let that sink in for a moment. A human-made spacecraft bristling with sophisticated instruments potentially flew through a stream of material ejected from an interstellar visitor. This could very well be the first time in history that we have ever directly sampled matter from another star system with in situ instruments. And yet this potentially groundbreaking story has been largely overshadowed in the broader coverage surrounding 3I Atlas. Let me explain precisely what happened and why its implications are so profound. Europa Clipper was launched in October 2024 on a meticulously planned trajectory that will take it to Jupiter, where its primary mission is to study Europa, the intriguing icy moon widely believed to harbour a subsurface ocean that might potentially support life. The spacecraft is currently in its cruise phase, traversing interplanetary space en route to a series of gravity assist manoeuvres that will eventually deliver it into the Jovian system. During this extended cruise phase, most of its scientific instruments are either in testing or hibernation modes. However, certain vital systems remain active for ongoing calibration and routine monitoring purposes. When scientists painstakingly calculated the orbits of both Europa Clipper and 3I Atlas, they uncovered something extraordinary. Their paths intersected in a way that would bring the spacecraft directly through the comet's extended tail. Not the dense coma close to the nucleus, but the immensely diffuse ion tail, that vast stream of charged particles and ionized molecules stretching for millions of kilometers behind the object, gently pushed outward by the solar wind. The tail, while extensive, is incredibly diffuse, far thinner than Earth's atmosphere, or even the best laboratory vacuums. But it is not empty. It contains individual atoms and molecules liberated from the comet material that undeniably originated in another star system, now streaming through space in a configuration that serendipitously allowed a spacecraft to encounter it. This event was not planned. Europa Clipper's trajectory was meticulously designed years before. 3I Atlas was even discovered, optimized solely for its primary mission to Jupiter, with no consideration for interstellar visitors. This encounter is a matter of pure chance, a cosmic coincidence of geometry and timing. But chance does not diminish its profound value. In fact, there's something almost poetic about an unintentional encounter, about the universe itself, arranging a meeting between cutting-edge human technology and ancient interstellar matter without any deliberate effort on our part. What instruments on Europa Clipper might have detected material from the tail? The spacecraft is equipped with an array of sensors specifically designed to study Jupiter's magnetic environment, including charged particle detectors and mass spectrometers capable of identifying chemical composition. While these instruments were not explicitly designed for comet encounters, they are sensitive enough that passing through even a diffuse tail could produce measurable signals. The challenge now lies in meticulously distinguishing those faint signals from the pervasive background noise from the normal charged particle environment of interplanetary space. That intricate task requires painstaking analysis, carefully comparing data from the encounter period to baseline measurements taken both before and after. As of now, NASA has not released definitive results from this unprecedented encounter. This does not imply that it didn't happen or that nothing was detected. It simply means the data is currently undergoing rigorous analysis, meticulous validation, and painstaking comparison to established models. Space data analysis is a slow, deliberate process. One doesn't simply glance at a graph and immediately comprehend its meaning. One must account for instrument response, meticulously calibrate against known sources, and scrupulously rule out artifacts or noise. Absolute certainty is paramount before announcing findings of such immense significance. The scientific process is inherently slow and deliberate, especially when analysing something as unprecedented as this. But imagine what it would truly mean if the analysis unequivocally confirms the detection of tail material. It would represent the first direct sampling of interstellar matter by a spacecraft. We have previously collected interstellar dust using high-altitude aircraft, capturing minute particles that passively drifted into our solar system and were scooped up in Earth's stratosphere. But that is passive collection, random particles that happen to find their way to us. This would be fundamentally different. This would be an active encounter with a known interstellar object, a direct passage through its outflow, an in situ measurement of its composition. The resulting data could reveal insights that remote spectroscopy simply cannot provide: isotopic ratios with exquisite precision, the detection of trace elements or compounds too faint for distant observation, and direct measurements of particle sizes and charges within the tail. That compositional data would be invaluable for understanding not just 3I Atlas specifically, but interstellar material generally. It would provide critical ground truth for calibrating remote observations. When one possesses confirmed knowledge of the actual composition of material in the tail, one can more accurately interpret spectroscopic data from distant observations, thereby refining models of how different molecules produce their unique spectral features. This creates a powerful feedback loop where direct and remote observations mutually reinforce each other, each making the other more profoundly valuable. The Europa Clipper encounter also serves as a compelling proof of concept for future missions. If Europa Clipper travelling for an entirely different purpose could unintentionally sample an interstellar visitor's tail, then dedicated missions could certainly achieve this intentionally. We could in theory design and launch spacecraft specifically engineered to intercept newly discovered interstellar objects flying directly through their comas or tails to collect pristine samples. Such missions would be incredibly challenging, demanding rapid response capabilities, as we typically only discover interstellar visitors once they are already relatively close. But they are not impossible. With sufficient preparation, adequate resources, and sufficiently early detection, we could potentially dispatch a probe to rendezvous with an interstellar object, studying it up close in ways that telescopes, however powerful, never can. Some visionary scientists have even proposed far more ambitious concept missions that would actively capture material from interstellar objects and return it to Earth. Imagine having physical samples from another star system in laboratories here on Earth, available for direct analysis with every cutting-edge technique chemistry and material science can offer. The knowledge gain would be extraordinary. We could study crystal structures formed in alien chemical environments, organic molecules that whisper tales of entirely different formation conditions, and isotopic signatures that tightly constrain the history of the material. A sample return from an interstellar visitor would undoubtedly rank among the most significant space missions ever undertaken. For now, we await the conclusion of Europa Clipper's data analysis. When NASA eventually releases its results, if they confirm the detection and characterization of tail material, it will be a major story. It will represent a significant milestone in interstellar object research, a powerful new technique added to our ever-expanding toolkit for studying visitors from beyond. And it will have unfolded during the very same year that 3i Atlas makes its closest approach, thus solidifying 2024 as a landmark year in this nascent field of astronomy. Even if the encounter data proves ambiguous or fails to show a clear detection, the mere attempt is inherently valuable. It profoundly informs future planning. It tells us precisely what signals to actively search for, what instrument sensitivities are truly needed, and what formidable challenges exist in distinguishing cometary tail material from background noise. Every observation, whether overtly successful or not, teaches us something vital that makes the subsequent one better. The Europa Clipper encounter also powerfully underscores the deep interconnectedness of space exploration. A mission meticulously designed to study a moon of Jupiter ends up contributing profoundly to our understanding of interstellar objects. Data gathered for one specific purpose finds invaluable applications in another. Instruments meticulously built for specific targets prove remarkably useful for unexpected encounters. This inherent versatility is a fundamental reason why space missions, despite their immense cost and complexity, are profoundly worthwhile. They don't just answer the questions they were initially designed to address, they enable serendipitous discoveries, unplanned observations, and crucial connections between seemingly disparate areas of research. As December 19th approaches, the Europa Clipper encounter adds another compelling layer to this evolving story. We have already, in a sense, potentially touched this interstellar visitor, sampled its outflow, recorded its subtle signature. The Close Approach Observation campaign then builds upon that, providing complementary data from an entirely different perspective. Together, the spacecraft encounter and the telescopic observations create a far more complete and nuanced picture than either could achieve alone. That is the inherent beauty of multi-method science, approaching profound questions from multiple angles, combining diverse techniques and platforms into a single coordinated investigation. The story of 3i Atlas, then, is not merely about a comet gracefully passing through our solar system. It is perhaps more significantly about humanity's rapidly growing capability to study such objects, to detect them early, to coordinate international observations, and sometimes even to physically encounter them with our advanced machines. It is about the profound progress in our collective ability to investigate the galaxy, beyond our immediate neighbourhood, to treat interstellar space not as an unreachable void, but as a dynamic realm we can actively study, potentially sample, and perhaps one day even visit. It is about the ever-expanding horizon of what is possible, what is knowable, what we can learn about the universe through relentless persistence and boundless ingenuity. Let's now bring all these threads together. All the pieces we've meticulously explored: the object itself, the observations, the fervent debates, the tantalizing possibilities, the serendipitous encounters, and collectively consider what December 19th truly signifies for humanity. Not just for astronomers, not just for this particular comet, but for us, as a species, progressively learning to perceive ourselves within a grander cosmic context. Step back from the intricate details for a moment. Forget the complex spectroscopy and the precise trajectory calculations and the vigorous debates about natural versus artificial. Focus instead on the simple, yet utterly profound fact at the heart of this entire story. On December 19th, something that originated around another star will make a close pass by Earth, and we as a civilization will be watching. We possess the remarkable technology to observe it, the accumulated knowledge to interpret what we are seeing, and the inherent curiosity to deeply care. That unique combination is quite simply historically unprecedented. For the vast majority of human existence, the night sky remained an inscrutable mystery. Stars were distant lights whose true nature we could not fathom. Comets were perceived as omens, harbingers of fate not understood as physical objects adhering to predictable paths. The very concept that anything could originate from beyond our solar system, from the immense void between stars, was not even a notion for which people possessed the vocabulary to express. We were confined by the boundaries of our ignorance, perceiving the universe as small, local, and firmly centered on Earth. The monumental expansion of that perspective, the profound realization that we are merely a planet among countless planets, a star system among innumerable star systems, a galaxy among a universe of galaxies, is arguably one of humanity's greatest intellectual achievements. 3i Atlas represents precisely where that achievement has brought us. We can now actively detect objects from other star systems as they traverse our own. We can meticulously study their composition, their behaviour, and their distant origins. We can ask fundamental questions. Where did they come from? What conditions gave rise to them? What do they reveal about planetary systems beyond our own? These are no longer purely philosophical questions. They are robust scientific inquiries empirically answerable through meticulous observation and rigorous analysis. That transformative journey from primal wonder to profound understanding is what December 19th truly celebrates. But it is more than just a testament to scientific progress. It is about gaining perspective. Every time we study something that originates from beyond our solar system, we are powerfully reminded of the immense scale of space, the unimaginable age of the universe, and the vast, relentless processes that, while entirely independent of Earth, nevertheless adhere to the very same elegant physical laws. 3 Atlas formed around another star billions of years ago. It was violently ejected by some ancient gravitational interaction and has been ceaselessly travelling through interstellar space ever since. During that unimaginably long journey here on Earth, life slowly evolved. Dinosaurs rose and fell, mammals diversified. Humans eventually appeared, developed complex language, built intricate civilizations, invented telescopes, and now in this infinitesimally tiny moment of cosmic time, our species and this ancient cosmic traveller briefly cross paths. That reality is profoundly humbling, it is utterly awe-inspiring. It also tangibly connects us to the rest of the galaxy in a way that abstract theory never can. This is not some remote concept. It is a physical object composed of atoms faithfully obeying Newton's laws, entirely observable and undeniably real. It provides incontrovertible proof that the galaxy is interconnected, that objects routinely move between stars, that the perceived boundaries between stellar systems are permeable. We live not in isolation, but within a dynamic, interconnected cosmic environment where material and information flow, where today's interstellar visitor might carry tomorrow's pivotal insights. The ongoing debate about whether 3i Atlas could be artificial, whether we should even entertain that possibility, is ultimately a proxy for humanity's most ancient and profound question. Are we alone? It is the question humans have contemplated since we first comprehended that stars are in fact other suns. Are there others out there? Other minds, other civilizations, other species gazing up at their skies and asking precisely the same question? We simply do not know. We possess no confirmed answer. But the very act of asking that question, of taking it seriously enough to rigorously test it scientifically, is a fundamental part of what makes us human. We are inherently curious. We wonder. We yearn to know not just how the universe operates, but whether anyone else is learning alongside us. December 19th will not definitively answer that question. The odds that we'll find conclusive evidence of extraterrestrial intelligence in observations of 3i Atlas are undoubtedly low, but the sheer fact that we are looking, that we are treating this as a legitimate scientific question, rather than pure fantasy, that we now possess the sophisticated tools and methods to investigate it, that matters immensely. It signifies that we are seriously entertaining the possibility that we are not alone, that we are open to evidence if it appears that we are willing to have our fundamental understanding of the universe challenged and potentially forever changed. Even if 3i Atlas proves to be entirely natural studying, it serves humanity's long-term future. Understanding interstellar objects helps us gain a universal understanding of planet formation everywhere. It provides crucial insights into the raw materials available in other star systems, the complex processes that create icy bodies and rocky worlds, and the astonishing diversity of planetary environments throughout the galaxy. As we begin to seriously contemplate interstellar travel, as we envision humanity's eventual expansion beyond our home, solar system knowledge about what truly exists in the vast space between stars becomes profoundly practical. What hazards might we encounter? What resources might be available? What can we realistically expect to find? The observation campaign also serves as a powerful demonstration of genuine international cooperation. Space agencies from multiple countries, observatories spanning several continents, researchers freely sharing data, all meticulously focused on a common unifying goal. In a world too often fractured by politics and ideology, astronomy remains a remarkably unifying force. The universe, after all, cares nothing for borders or nationalities. A photon from 3i Atlas carries precisely the same information, whether it's detected in chilly Hawaii or in Earth orbit. Scientists from diverse nations collaborate seamlessly and naturally in this field, because the overarching goals are universally shared, and the profound benefits belong to everyone. December 19th is a global event in the truest, most inspiring sense. For young people, for students, for anyone intrinsically inspired by exploration and discovery, this event powerfully illustrates what is possible through the relentless pursuit of science and technology. Just decades ago, we lacked the capacity to detect interstellar objects at all. Today, we track them meticulously, study them, and have even sent spacecraft through their tails. That astonishing progress occurred because people collectively chose to build sophisticated telescopes, to develop groundbreaking instruments to tirelessly ask profound questions, and to doggedly pursue their answers. It happened because societies invested in scientific endeavour, because governments and institutions steadfastly supported research, and because countless individuals dedicated their entire careers to understanding the cosmos. The monumental work that renders December 19th so significant did not commence yesterday. It is the culmination of generations of concerted effort, and it continues. The children who are watching news about 3i Atlas today might well be the astronomers who discover subsequent interstellar visitors decades from now. They might design innovative missions that intercept such objects, that return precious samples that perhaps eventually carry humans to visit other star systems directly. The profound inspiration of moments like this feeds forward, nurturing future scientists, engineers, and explorers who will push the boundaries of knowledge and possibility further than we can currently even imagine. As December 19th approaches, take a quiet moment to truly reflect on what is happening. Really contemplate it. An object from another star, having journeyed for longer than human civilization has existed, is about to make its closest pass by our planet. We're going to observe it with instruments we meticulously built. We will strive to understand it with knowledge we painstakingly developed, and we will add its story to the grand narrative we are collectively writing about the universe and our unique place within it. That unequivocally is extraordinary. That is worth pausing to deeply appreciate. Whether you personally watch the sky, diligently follow the news coverage, or simply carry the quiet awareness that it is happening, you are an intrinsic part of this moment. You are living through a time when humanity can achieve things that previous generations could not even dream of. A time when we can reach out across light years, not physically but intellectually, and grasp something profound about worlds we may never visit and stars we will never stand beneath. That incredible capability, that expanding knowledge, that unyielding curiosity, these are achievements unequivocally worth celebrating. December 19th is a date, yes, but it is also a powerful symbol, a reminder that we inhabit a universe brimming with boundless wonders that we possess, the remarkable tools to explore those wonders, and that the magnificent journey of discovery never truly ends. There will be other interstellar visitors, other close approaches, other profound mysteries to investigate. This is but one compelling chapter in a story that is still being written, a narrative that will continue long after we are gone, one that powerfully represents humanity's ongoing relentless effort to understand the cosmos. So mark the date. Pay attention. Allow yourself to feel that profound spark of curiosity. And remember that you are witnessing something truly rare and remarkable. A fleeting meeting of two wanderers, one a vibrant planet teeming with life and intelligence, the other a silent cosmic drifter from unknown origins, passing briefly in the unfathomable vastness of space. That intersection, that singular moment of mutual presence is December 19th. And it matters profoundly because we are here to witness it, to understand it, and to forever learn from it.